start with sequential circuits. Yes, so what are basically sequential circuits? In previous, we know that combinational circuits are those whose output is dependent on the possible inputs at that time. But in sequential circuit, what happens is the output is also dependent on previous state of the circuit along with the current variables at that time. And for this, to storing this previous state of the clock circuit, we need a memory element, and that memory element is basically flip-flop. And flip-flops are of various types like SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. But on a basic root level, all of these flip-flops implement binary latch. Now what is binary latch? So binary latch is nothing but two NOT gates which are connected to each other in this configuration, which is known as cross coupled. And in practical, this binary latch is implemented using the NAND gate. Alright, and let's say these NAND gates belong to any of one IC. Then what will happen if we provide energy or if we provide the voltage to the IC, then the NAND gate who is having less propagation will give its output fast. So let's say this NAND gate gave it output as 1, and this one is will go to N2, and this N2 will produce the output 0. If the propagation delay of N2 is less, so it will provide 1, and this one will go to N1 and the output will be 0. So more or like the storage here is not very much dependent as per the user input. It is just dependent upon as per the propagation delay of the NAND gate which are used. So to store it as the user want, we need to now increase the hardware. Now to increase the hardware, we will be placing and we will be studying SR flip-flop first. Yes, it's visible. Yes. Okay. So first we will be studying SR flip-flop. The connection is like this, that this is one NAND gate, this is another NAND gate, and this is a binary latch they are implementing. Now in this binary latch, what we did, we provided another input which we are taking from user. This is called as S and this is known as R. So this whole flip-flop is known as SR flip-flop. This whole flip-flop is known as SR flip-flop, where S and R are nothing but binary variables. So if we just take the example, let's say it is 1 and it is 0, then this will generate output as 0 and R will generate output as 1, and this 0. And if you don't know about one property of NAND gate is that if any one of the input is 0, then the output is directly 1. If any one of the input is 1, let's say it is B, so it produces output as B complement. If let's say there are multiple inputs, 1, A and B, then the output is A, B whole complement. But here if there are multiple outputs, one of them is 0, then the output is directly 1. This is for NAND gate, NAND gate, NAND gate, NAND gate. Yes. So if the output is 0, then it produces the output as 1. So Q is 1. This Q is 1, so both the values are 1. So at 1, 1, the NAND gate produces the output as 0. So we can see that at 1, 0, it produces output 1. It is known as set operation. Similarly, if you just keep values and obtain the truth table of here is 0, 0, it restores the previous value as it has. How it like this? For example, 0, it produces 1. At 0, it produces 1. Now both values are 1, 1. Let's say this is Q. So here the answer would be Q only. So the output would be Q complement, same as the last input, last circuit value. And here also the output, the value from here go to Q0. So Q0 complement, then it will form Q only. So at 0, 0, it restores previous state. At 0, 1, it becomes output as 0. It is known as reset operation. At 1, 0, it is known as 1. It is known as set operation. At 1, 1, the input is not allowed. Why the input is not allowed? Because at 1, 1, both the output, let's say this is 1, this will be 0, this will be 0. So output would be 1, output would be 1. But we do not want the output terminals of the flip-flops are giving same value. We always want that the output terminals should be giving complementary value to each other. Therefore, the input 1 1 is never allowed. If you talk about the representation, then this is S, this is R, Q, and this is Q naught. One value, the other is complement of that value. Exactly. But we always talk about the circuit in the whole electronics with the clock. This is the clock pulse where on and off, and this is the time period of clock. There first from first on to off. Then this same repeats on itself. So if this is the previous state, then this is the next state, because here it is the next pulse will come here. So if we talk about that, the circuit only and only works when we have applied the clock, then how will it be done? So it can be done easily by just modifying hardware a little bit more. How hardware has to be modified? The input NAND gates, which were directly connected to user input, now has two inputs, and one of them input is a clock. Then the rest same is as before it was. So this is flip-flop is, and if we generally talk about any other flip-flop, then we are referring it with respect to the clock signal only. If we talk about the truth table, then if clock is 0, this clock is 0, then the output would be 1. If this is 1, it goes here. If it is Q and here it is Q naught, then this Q will come here. One of the input is 1, then what will be the output? Q naught only. And if this Q naught goes here, one of the input is 1, then what will be the output? Q only. Therefore it restores the previous state only. So if clock is not applied, then we don't consider S or R. Just now we saw. And it restores the last state only. And this is true for all the flip-flops which we are going to study. That if clock is not applied, irrespective of the value of S or R, it restores the previous state only and only. If clock is applied, then it is 0 0. If clock is applied 0 0 1, it is reset operation. If 1, then it is 1 0 1 set operation. And if all are 1, it is not allowed. It's same to the previous. My recommendation would be, if you are studying with me, then just keep writing some, just keep having some running notes. Alright, and I mean keep just noting, don't just watch it like movie series, because then it is quite difficult to understand. Alright, then let's talk about the representation. This is S, this is R, this is the middle clock which we are applying. And before that we have studied like this. Yeah, this table we studied. So this table is with respect to when clock is applied. Alright, yes. Okay, so let us suppose that we are applying clock. Alright, if we are not applying clock, so it is 0, and we just get the last value only and only. But what if I intentionally want that before applying clock, the output should be 0, the output should be 1? Then how to modify and how to get there? So this can be done easily. How? We need to modify the circuit more, and this modified circuit has now 3 input NAND gates, and one of the input terminal is known as preset, and the input terminal is known as clear. For the time when clock is not applied, this preset and set values cannot be equal to each other. Alright, so when clock is not applied, it is 0, it is 1. So if preset is 0 and clock is 1, if one of the input of the NAND gate is 0, then the output is 1. So clock, this Q will be 1, this 1 will go here, and the output of the clear terminal is we have set to 1. So this is 1 and 1. Now both of the terminals of this NAND gate are 1, and if we have not applied the clock, this is 0. So this will be coming as 1. So 1 1 1, the output will be 0 only. So by default, before applying even the clock, we can set the values of the circuit as 1 and 0 also using preset and set. Similarly, if I apply preset as 1 and clear as 0, preset and clear, not preset and set, it is preset and clear. If I apply preset as 1 and clear as 0, then this would be 1 and this would be 0. If any of the input to the NAND gate is 0, then the output is 1. So the Q naught will be 1. This will go here, this is 1, this is 1. If clock is 0, this will also 1. So 3 terminals of NAND gate are 1, therefore the output will be 0 only. So When this is 0 and this is 1, it is known as preset operation. When preset is 1, clear is 0, it is known as clear operation. For normal operation, when we just apply clock, the preset and clear terminals are known as are made 1 and 1 respectively. Alright, and preset and clear value 0 and 0 are not allowed. And this is preset and clear are not equal to each other when clock is not applied. At that time, we cannot have preset and clear as equal values. It is moreover like active low preset and clear values, which we studied in before topic now. So it is moreover like active low preset and clear. So the representation is like this bubbled symbol here, and this is preset and this is clear. By default, if we are just saying it is active low preset and clear, and active high, we will not have the bubble symbol. So we do not have to get into the details of that if you are studying for CS gate or anything. Okay, so now what next difficulty we have is that we cannot have output when we have input terminals as 1 and 1. Then how to get it? And for any other electron that you have output for all the defined inputs. So for that we need to modify what it is that we used input NAND here, input NAND gate, and like it was one you put, this was there, this clear, one terminal going to here, and this producing output Q, which is output as Q0. Now this Q0 along with going input to this NAND gate, it will also have one of the input going to this before NAND gate, input NAND gate, and this Q will have the one of the input to the before NAND gates, like this. Alright. So if the clock is 0 for all flip-flop, the next state is coming to be as same as the previous state, which I have already said to you. So when clock is 0, it is last state. When clock is 1, we have all 0, 0, 1, 0, it is 1. It is 1, 1, it is Q0 only. How this is Q0? If you just apply the values here, for example, this clock is 1, yes, this is 1, this is 1. So when both of the inputs of the NAND gate are 1, it produces the output. What? Complement of the its third input. So what is that third input? This is Q complement. So it will form Q, and it will be forming Q complement. This Q will go here, and this is Q and Q0. When NAND gates, so this is not equal inputs, so it will form Q0, and this will form Q only. Alright, like from here, equal inputs. Here it will forming the Q0 only, and here it will be coming from Q0 only. So both will be forming Q0. And always remember, just know one thing: if we are talking about the input and output, the input are these. Alright, the output, if we are saying about any of the flip-flop, then the positive one we are always referring to as its output. For example, here the positive one is Q only. So we are already and only referring Q as our output. So that's why if the value here is coming Q complement, so we are saying the Q complement as our output. Right. So if we talk about the representation part, then this is our representation. Like this is preset value, and this is J, K, Q and Q0. Alright. If when clock is applied, the what will the truth table of G clock? It is 0, 0 at Q0, 0, 1 it is 0, 1, 0 it is 1, and 1, 1 it is Q and complete. Q n the last state, and current state is n plus 1. So it is a terminology to write and understand. First is logic circuit, second is truth table, third is characteristic equation, and the fourth is excitation table. The logic circuit and truth table we have already seen. Now it's time for the characteristic equation and excitation table. Now what are these? Characteristic equation is nothing but a mathematical equation which represents our truth table. Like the truth table comprises of rows and columns and all that. Every time when we have to see or understand it, we have to draw that all those. So instead of that, if we can represent the same information in compact equation, that equation is known as characteristic equation of the flip-flop. So first we are studying about SR flip-flop. This is the SR flip-flop table. If you just make SR Qn, and this is Qn plus 1. This is not nothing new columns or nothing. The inputs which we have studied in their truth tables, like which we studied before. Now we just see that where to apply when, like this is S, this is R, this is output Qn plus 1, 0 1, it is 0, it is 1 0, it is 1, and it is 1 1, it is not aligned. So when we are forming at 0 0 0 Qn, and this we have written on the copy, so 0 0, the output is Qn. What is the Qn? 0, so it's written here. 0 0, what is the output? Qn. What is the Qn right now? 1, it is written here. 0 1, the output is 0, 0 1, the output should be 0. So this way we have made all this table, and if you just write the 1, this is equivalent to 0, this is equivalent to 1 in decimal. So if we just write it in the form of midterms, so it will form 1 4 5 1 4 5, and don't get condition are 6 and 7, don't get condition 6 and 7, and using K-map we will simplify, and we will finally be getting that Qn plus 1 is equal to S plus RQn. Alright, S plus RQn, S plus RQn. Alright, it's visible. Yes. So if we see about the characteristic equation of JK flip-flop, then this is the whole of our table, and we just have written midterms. The characteristic equation of J is basically JQn plus K bar Qn. Alright, remember always that this K is the one whom, and for R, you remember, what should I show you? Yes, so just keep writing them. So this is S plus R Qn, S plus R Qn. Alright, now let's talk about excitation table. Let's talk about the excitation table. Yes. Basically, excitation table is the set of all inputs which tells that from present state to some another next state or final state or whatever the state could be, what are the set of inputs that would be required to do so. Alright, so it is a takeaway from the excitation table. The normal truth table just tells about this input, this will be output, this input, this will be output. It is the representation that on these input it will move from this state to this state, or we can understand if we are moving from one state to another state, and what are the set of inputs. The excitation table gives you that. Alright, so Qn plus 1, this is a representation. These are we will be seeing S and R value. So 0 to 0, what possible combination is 0 to 1, 1 to 0, 1 1. Yes. So it means we are going from 0 state to 0. We are going from 0 state to 1. We are moving from 1 state to 0. Basically, these are state values, that if one of the state value this, and we are going to another state who are having value this, and what are the inputs to these. So using the truth table, from this we can see that we can go to 0. We can go to 0 having input 0 and 1. 0 and 1. We can also go to 0 if only previous state, this is current state. So if I say 0 0, it will go to previous state only. So similarly, if we form the whole excitation table, it would be like this only, that 0 like this, and now we can see that here anything can be there, and this only 0 need to be present. Similarly here S, the value of S should be 0, R can be anything only. So we have now written all this, like for JK also, like S, the value can be 0, R can be anything. For 0 to 1, it could be 1, it could be 0. It is 0, it is 1, and for 1 1, it can be anything. R just need to be 0. Yes, you can remember it like 0 1 0, don't care, and then it will go reverse, don't care, 0 1 0. It is very important to just keep remember this for the later time. Yes, for JK flip-flop, if I see this is the whole table, we will make 0 to 0, 0 to 1, 1 to 0, 1 to 1, and this whole can be implemented. This is 0 1, anything can come here, anything come here, anything, don't care basically anything I am saying. This is 1 and this is 0 only. Alright. Yes. So we are, it's visible. Yeah, it is. Alright, so basically now let's talk about something known as race around conditions in JK flip-flop. Race around condition in JK flip-flop, yes. So let me consider a clock pulse width. This is clock pulse width here to here. It is known as clock pulse width, yes. It is 8 microseconds, and let's say we have a propagation delay of flip-flop which is 2 microseconds. Basically you will be getting output